We would like to go over kinematics of rotational motion in this video. So first we have to introduce the concept of rigid object. By definition, a rigid object means there is no relative motion between parts of the rigid object. Now let's look at this ice skater on ice. So if he keep this pose and spinning, we would treat him as a rigid object. But if he put his hand down, for example, if he put his hand down, so there is a relative motion between parts, which is his hand and his other parts of the body, then he's not a rigid object anymore. So a rigid object means there's no relative motion between any parts of the object. Okay, now after we define rigid body, we can define rotation. First, we should have axis of rotation. Now, if you have axis rotation, then any points on this rigid object has to rotate on a circular path, so it's a perfect circle around this axis of rotation. So point B is also a perfect circle. So the distance between any points on the rigid body to the rotation axis doesn't change. And they all rotate. So if A rotates 90 degrees, B also rotates 90 degrees. That's how it works. So we can define angular displacement after we define the rotational motion of rigid body. So if you have one point, you have axis of rotation. You will see this point can only rotate on this two-dimensional plane perpendicular to axis of rotation. So in this case of CD, any points on the CD can only rotate in the plane of the CD. And any point where it's rotating its distance to the rotational axis doesn't change. Now after this is pretty simple. So that the angle it rotates, so the angle that object rotates, any point rotate from here to here, then that's angular displacement, and angular displacement actually should have a direction along the axis of rotation. By convention, we would call any rotation counterclockwise rotation to be positive and clockwise rotation to be negative. And for rotational motion, we're going to use unit radian instead of degree for angle. After we defined angular displacement, we just define angular velocity. Average angular velocity equals angular displacement over the time it takes. Just as if you recall, we define average velocity to be displacement, that x is displacement, and time it takes. So there is a 1-to-1 correspondence. Now, of course, the unit for angular velocity is radian per second. After we define angular velocity, we can also define angular acceleration. Angular acceleration is change in angular velocity over time it takes for this change. So final angular velocity, initial angular velocity over the time it takes gives us angular acceleration. Change of angular velocity over time it takes gives us angular acceleration. And its unit is radian per second squared. So if you recall, we define acceleration to be change of velocity over time it takes. So you can see there is a 1-to-1 correspondence between linear motion and rotational motion. If we have displacement in linear motion, we have angular displacement, initial velocity, initial angular velocity, final velocity, final angular velocity, acceleration, angular acceleration. And on the right hand side is all Roman letters. And left hand side except time t, we use Greek letters for rotational motion to make distinction. And theta, omega 0, omega, alpha. Now we learned 4 or maybe 5 kinematic equation for constant acceleration in linear motion. All of you should be expert on this right now. And because there is a one-to-one mapping between linear motion kinematic variables and rotational motion variables, there is also a one-to-one mapping between the kinematic equation. So final angular velocity equals initial angular velocity plus angular acceleration times t, corresponding to first equation. So same thing here. It's a one-to-one mapping. So if you have no trouble solving equation here, you should be good on this one too. So here's what we should do for rotational kinematic problems. So first of all, you need to make a drawing, and you need to decide which direction to be positive. So usually we take counterclockwise rotation to be positive and clockwise to be negative. Then you need to write down values that are given in this problem. There are at least 3 variables being given. So after you find these 3, you should pick an equation that relate the 3 known quantity to the quantity that the problem is asking. Sometimes you might have 2 possible answers, especially you are using the last kinematic equation here because it is quadratic. If you do a square root, you might get 2 answers. So let's see one example. We have a wheel rotate with a constant angular acceleration 2, so the angular acceleration is 2 radian per second square, and it turns through 2.4 revolutions in a 2-second time interval. So t is 2 seconds. Turning through 2.4 revolution will give us angular displacement. 2.4 revolution should give us 1 revolution means is 1 complete circle, so is 2 pi. 1 complete circle is 2 pi, so 2.4 revolution is 2.4 times 2 pi radian, give us 4.8 radian. 4.8 pi radian. Okay, and it asks us for final velocity. So which equation we should use? So I would pick this one. And if you have a 5 sets of equations, then you should know there's another one, which is theta equals omega t subtract 1/2 of t. You can use that one, but I think we can solve using the third one here, which I'm circling right now. We can use this one to solve omega 0 first, then solve for omega. So using that one, you should have angular displacement equals omega 0 t plus 1/2 of t squared. If you plug in all the numbers, you find omega 0 is 5.5 radian per second. The final velocity is omega 0 t plus alpha t, 9.5 radian per second. So this is just what you did for chapter 2. First, you figure out what are the 3 quantities that know. You find the quantity that which is asking. You find the proper equation to relate these 4. You have to find the equation containing those 4 variables, and you solve the variable which is not known. Should be very straightforward. Now, there's a way to relate rotational motion and translational motion or linear motion. So for a circle, if that's your radius, you rotate the angle theta, and the distance you move along the arc S should be related to this angle, and radius is S equals R theta. So the definition of velocity is this displacement over time. Displacement is R theta over t, and theta over t is angular velocity. So apparently Vt is R times omega. In the same way, you will see acceleration. Acceleration equals change of velocity over t. Now final velocity is r omega, initial velocity r omega 0. So you have this one, but you have omega, subtract omega 0 over t should give you alpha. So we call this one tangential acceleration, r alpha. Tangential acceleration means acceleration is tangent to the direction of motion. So tangential velocity is also tangent, is always tangent to the circle. Vt here and your at in the same direction of Vt. V tangential velocity and tangential acceleration. Now recall for circular motion, we would always have centripetal acceleration always pointing to the center of the motion. AC, if you recall, it should be Vt squared tangential velocity over r. And if you replace Vt with r omega here, you find it also equals r omega squared. Okay, let's do one example which relate angular acceleration and angular quantities and tangential quantities. So you have a helicopter blade, you have point 1. We know is speed, we know is angular acceleration. We want to know tangential speed, tangential acceleration, and total linear acceleration. So the angular velocity 6.5 revolution per second. If I do a unit conversion, I should have one revolution is 2 pi radians. So I should have 40.8 reading per second. This is for angular velocity. Angular acceleration, I do a conversion. It should give me 8.17 reading per second. So apparently I should have tangential velocity for 0.1 radians times angular speed 122.4 meter per second. A tangential acceleration is r times omega 24.5 meter per second. So it also asks me for total linear acceleration. And what's that? Total linear acceleration means this point you have actually two distinct accelerations. So this is tangential acceleration, is tangent to the circle, and then you should also always have centripetal acceleration, and the A total should be the vector sum of tangential velocity plus centripetal acceleration. So we first need to calculate what is centripetal acceleration, which is Vt squared over r, and we find it's almost 5,000, 3.9 meter per second square. No, just second square too. So you do a Pythagorean theorem of total, A total equals AC square plus A tangential square. And if you plug in all the number, because this one is dominating, you should roughly get 3.95 meter per second square.